We've talked about one-dimensional motion, okay? Things rolling along a table, things going straight up and straight down. Well, that's great, except for one thing. We have to have multiple dimensions. Life is three-dimensional. We're only going to talk about two dimensions, but the same principles work for three dimensions. The biggest principle that we have here is orthogonality. I'm just going to say two perpendicular dimensions are orthogonal in physics. And what that means is they're independent. They're perpendicular and independent. This is my symbol for perpendicular, but the very important part is independent. And that's so nice because that means that we can solve those two problems separately. Let me give you an example. Let's say, okay, let me just cut right to it. I've got a person down here throws a baseball. Okay, and that baseball goes up and down. That's two dimensions, right? It's not a straight line. The way the physics behaves is based on forces, for example. Things respond to forces. Well, the only force when that ball is in the air is the force of gravity. Okay, there's nothing else touching it. If we ignore air resistance, there's nothing else touching it. So the only force is in that direction. And as a result, that ball isn't going to speed up or slow down in this direction. So in the horizontal or the x direction, it will not speed up or slow down. It will not accelerate. It will continue moving at a constant velocity. So if we draw the velocity vectors on this, we can think of the horizontal and the vertical velocity vectors. At the beginning, yes, I grant you that it's moving in this direction, but it has a velocity in this direction and it has a velocity in this direction. When it gets over here, it's got that same velocity. In fact, anywhere, it's got that same horizontal velocity, but it's got less vertical velocity. It's slowed down. Gravity is slowing it down. It has downward acceleration. Up at the top, the velocity is 0 vertically. It's definitely moving this way, but it has 0 vertical velocity. Then this increases and increases. Okay? So the vertical is a constant acceleration. The horizontal is a constant velocity. And that's only because we have gravity. If we turned off gravity, this thing would move up like that. Okay? Alternatively, maybe we'd have a wind in this direction. If we have a strong wind in this direction, there'd be an acceleration in this direction, and these would be different. We'd have to account for the acceleration horizontally for the wind. But the bottom line is you set up a horizontal, or I'm sorry, I shouldn't even say horizontal, because you could be looking down on something accelerating. You set up two perpendicular axes and two frames of reference. Sounds complicated, but it really isn't. I'm going to show you with a fairly easy starting off part, and we call this a horizontal takeoff problem. Horizontal takeoff problem. Okay? And this is going to be a ball rolling off a table. Okay? I'm going to make the table something really convenient. I'm going to make the table, I'll say it's off a wall, and it's 5 meters high. Okay? And I'm going to say this thing is going 3 meters per second in that direction. And we want to find out where that thing lands. It's going to have a parabolic shape like this. Okay, and I want to find out how far away it lands. Well, looks really hard, but it's not that bad if we break it down into its different components. So horizontally and vertically, I'm going to break it down. Okay, horizontally, what do I know? Well, first of all, let's do it the way we solved acceleration problems. I'm going to pick a frame of reference. I might as well pick a frame of reference for vertical. Everything seems to be going down. I'm going to call down positive for vertical. So in 2 dimensions, I have to pick 2 positive directions, 2 frames of reference. And yeah, you could pick that positive, you could pick that positive. It's okay, as long as you're consistent. So horizontally, what we've got is we've got a velocity of 3 meters per second. We're looking for the horizontal displacement. Let me write that up there. Delta x equals question mark. You could say, well, that's really all we've got horizontally, except we know that this is going to be a constant velocity. It's not changing. It's not speeding up or slowing down. This is a very specific case called projectile motion. Projectile motion is 2-dimensional motion near a planet when there's gravity and no other forces on there. So after it leaves the table, there's no other force on it. So we know it's constant velocity in the horizontal direction, constant acceleration in the vertical direction. How do we use that? Well, V, I could write it like this. I don't tend to, but I could say, okay, my initial velocity is 3. If it's constant velocity, I know my final velocity is also 3, and my acceleration is 0. I don't tend to do it that way, but you absolutely can. That's perfectly fine, okay? If we do this, we really don't learn anything. We can't really solve. This won't get it for us. This delta x won't work out. You can try it. I'll leave that as an exercise. We need more information. But what I usually do is, instead of doing that, I just treat this as a constant velocity problem by just saying V average is 3. In fact, it's constant. Okay. So I would need the time to solve that problem. I don't have it yet. That's why we have 2 dimensions. That's why this helps. Vertically, I know the delta, I'm going to call it delta y, just to keep this separate, is positive 5. It goes down 5 meters during this trip while it's in the air. I happen to know that the acceleration is 10 in the positive direction. But I know one more thing. This is not going up or down at the beginning. There is no vertical velocity at the beginning. I don't know the final yet, but this is enough to let me solve for time. Notice, this is always going to be true for a horizontal takeoff problem. This is always going to be true, depending on the sign, what you pick for your positive, for projectile motion. So we've got those 3 variables. I can use the equation delta, instead of x, I'm going to write delta y equals v0t plus 1/2 at squared. I'm getting to the part of the board where I'm not as good writing because it's so low for me. And what I have is 5 equals 0 times anything is 0 plus 1/2 times 10 times t squared. When you solve that, you'll find the time is 1 second. So we use these 3 variables to solve for time. Well, guess what? It's in the air vertically for the same amount of time it's in the air horizontally. Time doesn't have a direction. Time isn't vertical, time isn't horizontal. So I can use that here. Time is 1 second. Then I can use, again, that simple equation. V average equals delta x over t. 3 equals delta x over 1. This ends up being 3 meters. To reiterate, to go over and make it a little clearer, a little simpler, for 2-dimensional motion, when it's projectile motion, if it's a horizontal takeoff, it's not going up and down at the beginning. You could think of it like this. Remember vector components? There's no vertical component. So what I tend to do is I tend to say it's constant velocity horizontally. That makes it easy. This is the easy side. This is the easy constant velocity equation. I pick my variables. I pick my frame of reference, of course, and I set up my variables, and then I solve. One of the big keys here that I want to highlight a little bit more is this, the time. The time is what the horizontal and vertical have in common. So for all these projectile motion problems, you're going to be solving one side and then using that time in the other side. So it's going to flow like that, or it's going to flow like that. You're going to do a lot of horizontal takeoff problems, you'll get much, much better at it. It becomes very easy. The angle takeoff problems are a little tiny bit harder, but once you have these down, you're in great shape.